This is Calculus 12, Chapter 4.3, Connecting f prime and f double prime with the graph of f. Use analytic methods to find the intervals on which the function is a increasing, b decreasing, c concave up, d concave down, e local extreme values, and f inflection points. So, this is our function, y equals to x cubed minus 12x. First, we have to take the derivative of our function. So we start by taking the derivative, which is y prime equals to 3x squared minus 12. After that, we have to find the roots of our y prime. So y prime should equal to 0. That means 3x squared minus 12 should equal to 0 as well. 3x squared equals to 12. X squared equals to 4, and x equals to plus and minus negative 2. Okay, so after that, we have to plug in those two roots into our original equation in order to find the increasing and decreasing function. And that is our critical point. Okay, so y negative 2 is equal to negative 2 cubed minus 12 times negative 2, which is equal to negative 8 plus 24, and that is 16. So we'll do the same thing for root 2, and then we'll get negative 16 as an answer. So our function is increasing from negative infinity to negative 2, and from 2 to positive infinity. And our function is decreasing between negative 2 and 2. Okay. So we now have to find our concavity. To find our concavity, we have to take the second derivative of our function. And if y prime is greater than 0, so it will concave up. And if y double prime is less than 0, it will concave down. So the second derivative, which is y double prime, is equal to 6x. And our critical points are x is equal to plus and minus negative 2. So y double prime negative 2 is equal to 6 times negative 2, which is negative 12. And negative 12 is less than 0. So that means that will concave down. And by concaving down, it means that it has a local maximum. At negative 2. So we'll do the same thing with y double prime 2. So that will be 12. And 12 is greater than 0. So that will be concave up. And when it's concaving up, it means that it has a local minimum at 2. Okay. So once we found out the concavity and our local extreme values, we're left to find our inflection points. To find the inflection point, we simply have to take the second derivative and we have to equal that to 0. So y double prime should equal to 0. So 6x should equal to 0. By that, x is equal to 0. And that was the answers for this question. I'm just gonna go back to the part A and B to explain to you guys what those brackets mean and where our function is increasing or decreasing. So we use our first derivative, which is 3x squared minus 12. And we have to use some points where they're between the critical points and infinity. So based on this question, we're going to use -3, 0, and 3 as our points. And we plug them into the first derivative. So it's y prime of -3, y prime of 0, and y prime of 3. Okay, and so that would be 3 brackets -3 squared minus 12, and we do the same steps for those two. Okay, so the answer for the first one is 15, for the second one is -12, and for the third one is 15. So -3, which is between negative infinity and -2, our function in that area is increasing because y prime is less than 0. 0, whereas between -2 and 2, and our function in that area is decreasing because our y prime is greater than 0. Sorry. That is actually greater than 0, and that is less than 0. So same here, 3 is between 2 and positive infinity, and we got positive 15, which means it's increasing because y prime is again greater than 0. So we see we have y prime greater than 0 and y prime greater than 0 and y prime less than 0. So we can say between negative infinity and -2, our function is increasing, and between 2 and positive infinity, as our function is increasing as well. So the only area that our function is decreasing is where our function is between -2 and 2. And that completes our lesson. Thank you.